We usually think of the lunar South Pole as a chaotic, cratered wasteland defined by the massive South Pole Aitken Basin, but data from Pragyan shows the ground beneath the rover isn't what it seems. It is actually a preserved, ancient surface that predates the Moon's largest impact structures. If you look at the orbital maps of the Shiv Shakti Point landing site, it appears to be a relatively smooth highland plain. But interestingly, when researchers from the Physical Research Laboratory in Ahmedabad began processing the Navcam and Chandrayaan 2 high-resolution camera data, they found something else. The landing site sits directly inside a 160-kilometer wide buried crater. This isn't a fresh crater with sharp rims. It is a ghost feature, almost entirely filled in by ejecta from the South Pole Aitken, SPA, basin impact. And essentially, this changes how we interpret every chemical reading the rover took. Because this crater is so old, it acted as a deep structural trap for materials that existed before the SPA event. So, when the rover moved across its 103-meter track, it wasn't just rolling over surface dust, it was traversing a graveyard of lunar history. The digital elevation models generated from the mission data show that this specific region has been hit by at least 2 major waves of debris. First, from the ancient 160-kilometer impact, and second, by the ejecta blanket of the SPA basin. But I guess the question is, why does a buried crater matter for modern science? It matters because the soil here hasn't been significantly disturbed for billions of years. By landing in this specific depression, the mission effectively gained access to a vertical cross-section of the Moon's crust without having to drill. It turns out that the smooth landing site was actually a deep window into the lunar past. And as you can see from the topographical analysis, the rover was parked on a unique geological boundary. To the north, the terrain is dominated by younger volcanic activity. But at the South Pole, within this buried rim, we are looking at the original building blocks of the lunar crust. But interestingly, the most disruptive data point didn't come from the landscape. It came from the chemistry of the soil itself. We have historically viewed the Moon as a volatile pore body, essentially a dry rock stripped of easily evaporated elements during its violent formation. But when the alpha particle X-ray spectrometer, APXS, and the laser-induced breakdown spectroscope, LIBS, began firing at the regolith, they found a massive spike in sulfur. In the equatorial samples brought back by the Apollo missions, sulfur is a trace element. But at the Shiv Shakti landing site, the concentration jumped to between 900 and 1400 parts per million. So we are forced to ask, where did it all come from? One possibility is that this sulfur is indigenous, meaning it was trapped in the lunar interior and brought to the surface by ancient volcanic outgassing. If that is the case, it suggests the lunar mantle is far more chemically complex than the early models predicted. And if you look at the LIBS data, which uses high-energy laser pulses to vaporize the rock, the sulfur signature was consistent across multiple points. It wasn't just a single salty patch of ground. It turns out the lunar South Pole acts as a cold trap, not just for water ice, but for a variety of volatile elements that would have boiled away at the equator. But just so we're clear, this discovery is still being debated. Some researchers suggest the sulfur could be the result of billions of years of micrometeorite bombardment, effectively seeding the surface with asteroid material. But I guess the real implication here is industrial. If we are going to build a permanent base, sulfur is a critical resource. It can be used for solar cells, batteries, and even a type of lunar concrete that doesn't require water. Essentially, India didn't just find a scientific curiosity. They found a potential fuel and manufacturing source for the next century of spaceflight. The high sulfur density at the South Pole breaks the old dry moon rule and sets a new baseline for what we expect to find in the permanently shadowed regions. It was long thought that the Moon's crust formed through a chaotic, piecemeal cooling process, but the Pragyan rover's traverse across the South Pole has essentially confirmed a much more unified, violent origin. By using the alpha particle X-ray spectrometer, APXS, to take 23 separate measurements along a 103-meter path, researchers found a chemical consistency that shouldn't exist if the Moon had a random geological birth. The data revealed a dominance of Faroan anorthosite, FAN, a specific type of rock that only forms under very narrow thermal conditions. But interestingly, this confirms the lunar magma ocean, LMO, hypothesis. The idea that shortly after the Moon was formed by a massive impact, it was a literal sphere of liquid rock. As this ocean cooled, lighter minerals like plagioclase floated to the top to form the crust, while heavier minerals sank to form the mantle. And if you look at the samples from the Apollo and Luna missions, which were collected from the lunar equator, they showed similar compositions. But just so we're clear, many scientists suspected the poles might be different. They thought the polar crust might have been contaminated by different volcanic flows or later impacts. But it turns out the Pragyan data shows the South Pole is chemically nearly identical to the equatorial highlands. So this uniformity across thousands of kilometers proves the LMO wasn't a local event. It was global. Essentially, the entire moon was molten at the same time. The rover's discovery of these magnesium-rich minerals at the surface provides the first in-situ evidence that the pristine crust of the moon is preserved at the South Pole. It's a massive win for the old-school models, but with a new twist. The South Pole is actually the best place to study the moon's original skin because it hasn't been resurfaced by the massive lava flows, or Maria, that we see on the near side. While we usually focus on the vacuum of space being cold, the lunar surface itself is surprisingly hot during the day. But data from the CHAS-TE, Chandra's Surface Thermophysical Experiment, probe showed that the heat of the moon is skin-deep. By deploying a thermal probe with 10 high-precision sensors into the soil, the mission recorded a temperature of 40 degrees Celsius at the surface, which is roughly the temperature of a hot summer day on Earth. But interestingly, as the probe moved just 80 millimeters into the regolith, the temperature plummeted to minus 10 degrees Celsius. That is a 50 degrees Celsius drop in less than 4 inches of dust. Essentially, this proves that lunar regolith is one of the most efficient natural insulators in the solar system. If you look at the data, the thermal conductivity is so low that the sun's energy cannot penetrate the top layer of soil. So this changes the water-ice conversation entirely. We used to think that water could only survive in the permanently shadowed regions, PSRS, where the sun never shines. But just so we're clear, this thermal gradient suggests that water ice could theoretically exist just a few centimeters below the surface, even in sunlit areas. The soil acts as a thermal shield, keeping the subsurface at a constant freezing temperature, regardless of the weather on the surface. And as you can see from the sensor readouts, the transition is sharp. This isn't a gradual cooling, it's a hard thermal wall. For future lunar habitats, this is a massive engineering advantage. Instead of building thick lead or metal shields to protect against the 100-degree swings of the lunar day-night cycle, we might just need to bury our structures under a few inches of local dirt. It turns out the moon provides its own insulation, and it's far more effective than our early orbital models suggested. It was long assumed that the moon was a dead world, a geologically silent rock that only rings when hit by a stray asteroid. But data from the ILSA, Instrument for Lunar Seismic Activity, has effectively challenged that silence. By deploying a cluster of high-sensitivity MEMS-based accelerometers directly into the regolith, the mission recorded the first ever seismic data from the South Pole. The instrument didn't just pick up the mechanical vibrations of the rover's wheels. On August 31st, 2023, it captured a distinct 4-second seismic signal that was entirely uncorrelated with any mission activity. So we have to consider that the moon's interior is still active. But interestingly, the signature of this event suggests it wasn't a deep moonquake, like those recorded by Apollo. Instead, it looks like a shallow crustal shift or a nearby micrometeorite impact. And if you look at the waveform, it shows how energy moves through the lunar soil. Because the regolith is so fragmented and dry, seismic waves don't travel like they do on Earth, they scatter. But just so we're clear, the detection of this natural event proves the South Pole is a tectonically noisy environment. This is a critical data point for the construction of future lunar bases. If the ground is shifting even slightly, our engineering tolerances for pressurized habitats have to change. Essentially, the ILSA data suggests that the lunar crust is under constant stress, likely from the Earth's tidal pull or the extreme temperature swings between day and night. It turns out the quiet moon is actually humming with microseismic activity. And as you can see from the frequency analysis, these events are frequent enough that they might pose a long-term wear and tear risk to heavy machinery. We aren't just landing on a platform, we're landing on a dynamic, shifting crust.